Imagine an employee gets a frantic call from their manager. The instructions are highly unusual, but the voice on the other end is unmistakable. Following orders, the employee opens the corporate safe, takes out the available cash, and deposits it directly into an untraceable Bitcoin ATM. The person who made that call was an imposter. Using a voice cloning model, the attacker had synthesized a highly accurate replica of the manager's exact speech patterns, generated entirely from just a few seconds of recorded audio. This bar chart shows the financial scale of the problem. In 2023 alone, attackers using these artificial voice models stole over $3.4 billion, primarily targeting seniors, small businesses, and nonprofit organizations. Because modern AI-generated voices have evolved to sound nearly identical to biological human speech, our ears are no longer reliable security filters against fraud. Our biological senses struggle to detect the deception. The tech industry's current primary defense mechanism against this vulnerability relies on audio watermarking. Systems like SynthID are programmed directly into large text-to-speech generators to tag the audio they produce. This standard audio waveform demonstrates the defense. Specific frequency bands are embedded deeply inside the audio, acting as a beacon for scanning machines. But if a bad actor strips away that watermark or uses an open-source cloning model, the resulting synthetic audio appears authentic to screening tools. Relying on embedded watermarks provides a fragile, passive defense. Effective security against voice cloning requires an active system capable of identifying artificial generation based on the audio itself, rather than a secondary tag. This new defensive approach utilizes a passive security application designed to run in the background of a user's smartphone or computer. When a phone call connects, the app captures a short clip of the incoming audio. It immediately normalizes both the volume and the bitrate, creating a uniform baseline across all data it processes. This diagram shows the crucial next step. The software converts this normalized auditory data into a distinct visual fingerprint. It reshapes the sound waves, folding them into a dense two-dimensional geometric grid pattern, similar to a QR code. Converting a linear auditory timeline into a static visual image allows the system to analyze the data differently. Instead of listening to a sequence of sounds over time, the software scans the architectural structure of the audio simultaneously. By translating sound into a visual format, the system can bypass the human conversational experience and look for specific patterns in the raw mathematical structure beneath. The core analytical engine scanning that visual fingerprint is a generative adversarial network, or GAN, a machine learning architecture where two neural networks effectively compete against each other to improve detection. The GAN is hunting for model artifact signatures. These are the unintentional micro-nuances and traces left behind by the artificial synthesis process. To recognize these traces, the model requires a baseline of authenticity. It is trained on datasets of real human speech, recorded across a spectrum of environments, various acoustic dynamics, and microphone types. It then undergoes adversarial training. The GAN is fed a variety of synthetic voices, forcing it to extrapolate and analyze artificial generation, so it learns the structural imperfections inherent to a voice clone. Because the GAN analyzes the microscopic characteristics of AI voice generation, it can identify synthetic voices without relying on human intuition or embedded watermarks. To see what this looks like in practice, we pull back to the user's perspective during the first few seconds of an incoming phone call. The moment the caller speaks, the GAN processes the visual fingerprint of their voice, calculating a probability score of its authenticity in real time. If the analysis suggests a high likelihood of a deepfake, a discrete pop-up alert appears on the device's screen. Much like a modern spam filter, the user receives an immediate visual warning that the caller's voice is likely synthetic. This alert system allows legitimate calls to continue, while giving the user a specific indicator to help them identify and stop a potential phishing attack. Because this technology processes audio in real time, the data pipeline is secured through encryption and decentralized computation to help keep personal information protected. The software utilizes a persistent learning loop. It optimizes its detection capabilities by analyzing patterns from previous interactions and storing those results to refine its future accuracy. This optimization process ensures that the detection software adapts as fraudsters develop new voice cloning techniques, keeping the system relevant against emerging threats. As bad actors weaponize AI to deceive us, Our safety depends on deploying intelligent, evolving systems capable of decoding the microscopic anatomy of sound, providing a necessary layer of verification for the voices we hear.